Hi, everybody. I just wanted to say a few words very briefly. Welcome everybody to the new series of colloquia this fall. I'm sorry we have to do it on Zoom again, but we decided for everybody's benefit, this is the best way for the moment. So the plan is to have all our colloquia on Zoom for the fall semester, and hopefully things will be better. And we'll be able to have in-person meetings. We'll be able to see each other again in our Jefferson 250 lecture hall. So please bear with us with this slightly awkward way of having our colloquia, but we hope it will be resolved relatively soon. So today we have a very exciting talk by Professor Avi Loeb from the astronomy department, and I would like to call on Doug Finkbeiner, who's more knowledgeable than I am, to introduce our speaker. So Doug, please.
It would be my pleasure. All right, hello everyone. Welcome to the first colloquium. Today, we welcome Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard and a best-selling author. He received his PhD in physics from Hebrew University of Jerusalem in Israel at age 24 in 1986. He led the first international project supported by the Strategic Defense Initiative and subsequently was a long-term member of the Institute for Advanced Study in Princeton. Professor Loeb has written 8 books, most recently Extraterrestrial, his second book this year, and about 800 papers on a wide range of topics, including black holes, the first stars, the search for extraterrestrial life, and the future of the universe. Professor Loeb is the director of the Institute for Theory and Computation, 2007 to the present, within the Harvard Center for Astrophysics. He's also the founding director and head of the Galileo Project, started this year, and he'll tell us a little bit about that today. He was the longest serving chair of Harvard's Department of Astronomy, most of the time I've been at Harvard actually, and the founding director of Harvard's Black Hole Initiative. He's elected a fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. Loeb is a former member of the President's Council of Advisors on Science and Technology, PCAST, at the White House, and a former chair of the Board on Physics and Astronomy of the National Academies. He's a current member of the advisory board for Einstein Visualize the Impossible of Hebrew University. He also chairs the advisory committee for the Breakthrough Starshot Initiative since 2016 and serves as the science theory director for all initiatives of the Breakthrough Prize Foundation. In 2012, Time magazine selected Avi as one of the 25 most influential people in space, or maybe on Earth, in the field of space. Anyway, without further ado, let's hear from Avi.
Thank you so much, Doug. I should start by saying that I don't assign significance to all these labels. As far as I'm concerned, I just maintain my childhood curiosity, and science offers a privilege of doing that. And especially if you have tenure, that's an opportunity to ask questions and learn about the world. So let me share my screen. Hopefully you can see it. And I'll just start with the slides. So most of the content of the talk today will focus on my book Extraterrestrial that came out about 7 months ago. And if I had to summarize it in one sentence, I would say, when you're not ready to find exceptional things, you will never discover them. On the right side of this slide, you see a textbook that we published with my former postdoc, Manasvi Lingam, a few months ago with Harvard University Press. It's more than 1,000 pages long, and it's intended to serve the scientific research on the frontier of the search for life, both microbial life and technological life in the universe. What you see on the left side is a photograph of a photograph that was taken by the German photographer Herlinde Quilbel and was presented in the hall of the Berlin Brandenburg Academy of Science and Humanities in October 2020. She came to my office at Harvard a couple of years ago and asked me to write on the palm of my hand the question that I regard as most significant in science. And I wrote, "Are we alone?" Now, I should tell you that the last 7 months since my book came out were quite tumultuous. I had of the order of 1,200 interviews with various media outlets. There were 30 film producers and documentary producers that contacted me for a follow-up project. There is, of course, the next book that we're now starting to write. I just wanted to advertise a few events that are complementary to what I'll describe today. In case you're interested, it's in the area. One of them is in the Library of Congress. There is the National Book Festival, and on Wednesday next week, September 22nd, there is a discussion, a Q&A discussion with Sarah Scholes that I will have at 7 p.m. And then closer to home, in the Coolidge Corner Theater in Brookline, on Monday, October 18th, there would be a book signing event at 6:15 p.m., followed by a lecture, and then the film Close Encounters of the Third Kind. So anyone interested is most welcome. And I should say that as I was preparing this talk just a couple of days ago over the weekend, I received this email from a rabbi in a congregation in Ann Arbor, Michigan, who posted a sermon for the high holidays. As some of you know, it's this period of the year. And the sermon was based on my book, Extraterrestrial. So that was a surprise to me that the content of this book touches on the religious beliefs of people. And a colleague of mine said, next time we meet for dinner with my wife, I will ask you to give a sermon. To which I replied, I would never lead a congregation whose members agree with me. Actually, another thing that happened today was that Congress publicized a call for a permanent office to address unidentified aerial phenomena. We'll talk about them. This just came out today, and you can see there was a news report about it that is dated September 13th, 2021, today. And it says, I mean, this call says that no later than 180 days from now, there would be a new office established by the Secretary of Defense to examine unidentified aerial phenomena. So that's a major development on the federal level. Now, the one thing I learned after decades of doing astronomy is that we should be modest, because not only we are not at the center of the universe, as the ancient Greek philosopher Aristotle argued, and of course it flattered the ego of everyone, so people believed him for 1,000 years. So now we know that we are not at the center of the universe. In fact, the universe doesn't have a center, but we are born into this world like actors put on a stage, and the stage is 10 to the power 26 times bigger than our body. And the play has been going on for 13.8 billion years. It's not about us. But moreover, in addition to that, we know that what we find in our backyard is not unusual. About half of all the sun-like stars host an Earth-sized planet roughly at the same separation. That we learned last year from statistics of data that came from the Kepler satellite. So again, we are not special. We should be modest. Nothing is unusual in our cosmic environment. There are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. Just think about it. It drives home the message that we should be modest. There should be cosmic modesty. So when I see a painting like the one in the middle of this slide of an emperor being very proud of himself after conquering a small piece of land, I smile, because it's no different than an ant hugging a single grain of sand on the landscape of a huge beach. That's not very impressive. And of course, I can understand where it's coming from, because when I watched my daughters grow up, when they were small, they were at home. And of course, they compared themselves to the other family members, and they thought very highly of themselves. They thought that they're the smartest in the world. And that point of view changed when we took them to the kindergarten, when they met other kids that might be smarter than they are. So our civilization will mature only by finding others. And one thing we know from observing the universe is the star formation history of the universe. Most stars formed billions of years before the sun. So if you combine that with the fact that about half of the sun-like stars have Earth-sized planet near them and circumstances are replicated there, then there could have been something like us 1 billion years ago. That would not be outrageous. You know, that would be just a sign of modesty from our perspective to assume that it happened. And of course, that civilization may not be around anymore. But if it developed to the point that we are at right now, or even better than us right now, then it would have developed artificial intelligence systems. Those are the systems that drive cars right now and will make medical decisions in the coming years and could outsmart us. So you can imagine sending them to space. They would replace astronauts. You know, in the past, we sent equipment that was not very smart into space, and we thought astronauts are needed to operate it. But if AI systems are intelligent enough, you don't need astronauts. In fact, it's much better not to send them, because natural selection did not allow us to survive in space. It developed us to the point where we exist comfortably on a planet like the Earth, but not out there where the conditions are much harsher. However, technological equipment could survive for billions of years in interstellar space. And if you imagine sending AI systems that are equipped with 3D printers, they could potentially replicate themselves when they land on other planets out of the raw materials that they find. And then within 1 billion years, they would be everywhere, because the travel time across the galaxy is much shorter than that. And so the question is, do we live in that reality where probes that are completely autonomous, they don't need guidance from their senders, because AI systems could be just like kids. You educate them early on through machine learning, and then you send them into the world and they learn from experience. So there is no need to communicate with them. In fact, it takes a long time to communicate with them if they cross interstellar distances. So do we live in a reality where lots of probes are filling up space? The only way to find out is by observing the sky. There is no point in arguing about it philosophically. And if you remember, 4 centuries ago, philosophers thought they know that the sun moves around the Earth. It seemed obvious. If you look at the sky, you see the sun moving. And then Galileo looked through his telescope and argued, no, I think the Earth moves around the sun. But the philosophers refused to look through Galileo's telescope. And not only that, they put him in house arrest. Today, he would have been canceled on social media. But that only maintained their ignorance. Irrespective of what they said, the Earth moves around the sun. So reality is whatever it is. You know, we can refuse to look through our windows, but that will not get rid of our neighbors. And this is the rationale behind the Galileo Project that we announced a month ago. And if I had to define it in one sentence, I would argue that extraordinary conservatism leads to extraordinary ignorance. And we should dare to look through our telescopes for the answers. Just a few months ago, there was an article published in Nature Astronomy, a very prestigious journal. It was written by a philosopher who was arguing that a very weird interstellar object that I'll speak about, Oumuamua, must have been natural in origin. And I looked at that paper and thought to myself, haven't we learned something over the past 4 centuries since the days of Galileo? It seems like it's not obvious for a lot of people to look for answers through telescopes. And the Galileo Project aims to address 2 major avenues of research. One thing to realize is that a meter-sized telescope can obtain a megapixel image of a human-sized object at a distance of a mile, roughly. And I actually searched online and found that you can add such a telescope to your bag. There is a button on an online website that sells such telescopes. It only costs $500,000, but apparently there are people willing to pay that, and you can click on add to the bag for $500,000. But that's something important to keep in mind, because there was a report delivered by the intelligence agencies to Congress on the 25th of June this year, suggesting that there are objects, real objects that were detected by multiple instruments in the infrared, in the optical, or by radar systems. So they appear to be real objects. About at least 143 of them could not have been identified. And it's not at all clear by the way they moved that they are human-made. Now, if we had a meter-sized telescope looking at them, we could have figured out whether they have a label saying made in China, made in Russia, or made on exoplanet X. It's not a philosophical question. So that's one major avenue of research that we will pursue, building telescope systems that include optical telescopes looking at reflected sunlight, infrared sensors that could operate at night if the object is warm, and then radar systems. And they will feed the data to cameras that will bring it to computer systems that will analyze it and look at targets of interest. We don't care about birds flying in the sky. I mean, I'm not a zoologist. Of course, there are people that care about them, and we will be glad to provide high-resolution images of birds to them. We also don't care about human-made objects. Again, I think there are people in residents of Washington, D.C. that care a lot about them, and I'll be glad to automatically transfer that data to them. They are as boring as birds are for this project. We are looking for something else. And then the second path of inquiry has to do with objects that enter the solar system from outside. Think of it as looking at your backyard for objects that came from the street, because it takes a long time for us to travel to the street. And the first such object was Oumuamua. I will discuss it. It looked weird, didn't look like a comet or an asteroid, the type of rocks we have seen before in the solar system. So we would like to find more. And next time, we want to fly a spacecraft equipped with a camera close to them so that we can get a high-resolution image and figure out their nature. And currently, I mean, I should say that I had many surprises over the past 7 months, and most of them over the past couple of months. There were a few multi-billionaires that visited the porch of my home. There was a YouTuber that flew all the way from California for a half-an-hour conversation. But altogether, we received close to $2 million over a few weeks without doing any fundraising. People just approached me. People that I've never met before approached me and said, here is some money for your research fund. And therefore, it allowed me to establish this project and assemble a group of exceptional scientists that are engaged in it. And after we announced it, there were thousands of people worldwide that sent emails with interest to contribute from their expertise. We have a website at Harvard that allows for crowdfunding, and we are grateful to the development office for cooperating with us. I should say that the higher administration at some point asked me, can you explain why this project is part of your day job? And I said, well, you know, if you look at my 800 papers, scientific papers, you would realize that almost all of them are about interpreting data obtained by telescopes. The Galileo Project is about interpreting data obtained by telescopes. Therefore, it's part of my day job. In astronomy, there is no lower limit to the distance of an object of interest. We study meteors, we study asteroids, we study interstellar objects. Even though they are nearby, they came from far away. And the administration agreed. So it's part of my day job. As I mentioned, the intelligence agencies delivered a report to Congress about unidentified aerial phenomena. And even the head of NASA, Bill Nelson, said that he actually saw the unclassified data when he was a senator. And he believes that scientists should look into that. And so I said to people under him, I'm happy to help you to make your boss happy. And since I didn't hear back from them, we decided to establish our own Galileo project where we will obtain open data and analyze it in the scientific way with an analysis that will be completely transparent and available to the public. I don't want to look at classified data because that would limit my ability to speak freely as a scientist. And it seems that this scientific approach is really needed because for 70 years, people talked about unidentified objects in the atmosphere. And of course, it may be a mixed bag. Perhaps most of them have mundane explanations. But just to remind you, it's sufficient to have one object that originated from an extraterrestrial technological civilization for this to have a huge impact on our society. So we don't, it's like a fishing expedition. We don't care about the sardines that we will find, those fish that we know about. We just want to see if we catch any fish that looks really unusual. And here is a photo album of the research team, exceptional scientists, mostly astronomers, some of whom you may recognize. For example, Alan Stern was the PI on the New Horizons mission. We have a scientific advisory board that you may also recognize. For example, if you're using Mathematica, the person who created it is on our advisory board, Stephen Wolfram. We have a philanthropic advisory board, and we are grateful for the generous donations that enabled this research. And we also have a public outreach affiliate. And finally, we have research affiliates, a lot of them, people that are interested in contributing from their expertise to the success of the project. So the big picture is that humanity's future is at stake. Currently, all our eggs are in one basket here on Earth. And it might make sense to spread them elsewhere. I call that Noah's spaceship, because as you may remember from the biblical story, in anticipation of the great flood, Noah built an ark and he put animals in it to save them from the great flood. Now, I'm not suggesting building a spacecraft and put whales and elephants on it, because that would be very complicated. I'm saying we can get the genetic code of the life forms that we care about, put it on an AI system equipped with a 3D printer. And once we know how to create synthetic life with that recipe, we go places and reproduce it. And since we can imagine doing that, they may have done that already. Now, Earth is our home, but only for a while. We have to recognize that, because there are internal threats, self-inflicted wounds, so to speak. The climate is changing, wars happen, pandemics, and other catastrophes that could destroy all the eggs in our basket. One thing I should mention, there was one person who escaped the Earth. I mean, at least part of his body escaped the Earth. That was Clyde Tombaugh, the person who discovered Pluto. So a small fraction of his ashes was put on the New Horizons mission that went to explore Pluto. Now, that doesn't make too much sense, because what are ashes? They are burnt up DNA. So we took the DNA that has some information content about Clyde Tombaugh, we burnt it up, and then this completely information-free product was put on the New Horizons mission to commemorate Clyde Tombaugh. That doesn't make much scientific sense. I don't know why NASA did that. It would have made much more sense to take the genetic code of Clyde Tombaugh and put it in electronic form on New Horizons. Or better still, to put a stem cell of Tombaugh on New Horizons. But we didn't do that. So if someone finds New Horizons, they will not think very highly of us. There are, of course, external threats. And they could come from asteroid impacts, solar flares, but eventually within 1 billion years, the sun will boil off all the oceans on Earth. And so we tend to build statues in the short term. For example, if you go to University Hall at Harvard, you see paintings of former deans and presidents that look very respectful of themselves, and they thought that by having a painting that preserves their physical appearance when they were alive, they will maintain longevity. Again, it doesn't make much sense, because within 1 billion years, everything on Earth will be burned up. So this will not survive very long. If you wanted to create a monument that would last longer than the sun, you would send an AI system that carries your guiding principles into space. And it could survive billions of years in principle and be your avatar. That would make much more sense than hanging a painting in University Hall. So we need to go to space. And let me just describe in a few words my personal journey from my childhood to space exploration. So I was born on a farm. I'm basically a farm boy still. 59 years ago, you can see a picture of me at age 7 on the top left. I used to collect eggs every afternoon. You can see the second photo showing that. And I used to drive the tractor. You can see me in the middle top photo with my sisters. I used to drive a tractor to the hills of the village and read philosophy books, because philosophy addresses the most fundamental questions that we face. Unfortunately, it doesn't provide an answer to most of them. If I move forward, I ended up at Harvard, got tenured, became the chair of the astronomy department. And then in May 2015, a black limousine parked in front of the entrance to the Center for Astrophysics. And out of it came an entrepreneur from Silicon Valley named Yuri Milner. He came to my office, sat on the sofa in front of me, and asked me whether I'm willing to lead a project to visit the nearest star system. And I knew that the nearest star system is 4 light years away. So it takes light 4 years to get to us from that system. And therefore, if you want to get there within a couple of decades, given our life expectancy, both Yuri and I are the same age, you need the spacecraft to move at 1/5 of the speed of light. And that's 1,000 times faster than a chemical rocket of the type that we've launched in the past, from Sputnik all the way to New Horizons. And a factor of 1,000 is a big factor. It's roughly the factor between Sputnik and the T-car that Henry Ford first produced. So I had to think about it for half a year, and eventually we ended up with a concept that seemed to be the only possibility with the technologies that we can imagine. And we announced it in April 2016 in the company of Stephen Hawking and Freeman Dyson, as you can see in the middle bottom photo. Oops. This is an artist's illustration of the solar system. You can see the sun on the left and the nearest star, Proxima Centauri, on the right. It's part of a 3-star system called Alpha Centauri. And halfway to the nearest star, there is the Oort cloud, which is made of the building blocks of the solar system, those bricks that were used in the construction project of the planets. Some of them were kicked around, and we see them in the Oort cloud. And it goes all the way to 100,000 times the Earth-Sun separation, roughly halfway to the nearest star. And if each star has an Oort cloud, they are very densely packed. And it turns out that the nearest star, Proxima Centauri, is 12% the mass of the sun. In fact, most of the stars are smaller than the sun. The sun is not a typical star. You might ask, why do we live next to a non-typical star? There may be a good reason for that, but we will not get to it. But this star, Proxima Centauri, has half the surface temperature of the sun, roughly 3,000 degrees Kelvin. It emits mostly infrared light. And turns out that it has a planet, Proxima b, that is 20 times closer to the star than the Earth is from the sun. Turns out that this is the habitable zone around this star. In fact, the surface temperature on the illuminated side of this planet is roughly the same as on Earth. So in principle, you could have liquid water there. But the planet is so close to the star that it's tidally locked, just like the moon is to Earth. You see always the same side of the moon. And Proxima Centauri sees the same side of Proxima b as it moves around every 11 days. So there is a permanent day side and a permanent night side. And my daughters say that if we ever go there, they want to have a house on the strip that separates the permanent day side from the permanent night side, because you can sit on the porch and see the sunset forever. Just think about it, seeing the sunset. The sun never sets in that strip. And I asked the students in my freshman seminar last semester, do you know of any animal that has infrared vision here on Earth? And the brightest student within a few seconds found this image of a shrimp that has eyes that look like ping pong balls connected with cords to the head of the shrimp. And she said, it looks like an alien to me. So how do we get there? Well, the method that the Starshot Initiative adopted is pushing on a thin film, which we call a sail, with a very powerful laser beam, pushing it with light. And if the sail is just a few grams in weight, and the laser beam is about 100 gigawatt, then over a few minutes, you can launch the sail to a fifth of the speed of light. And you can attach electronics that you find in a cell phone, a camera, communication device, navigation device to this sail. And here is a video that demonstrates the concept. There is a mother spaceship that releases a sail above the atmosphere so that it doesn't encounter the friction with the atmosphere, and an array of many low power lasers combine their beam to a very powerful beam of 100 gigawatt or so, shining on this sail that is roughly the size of a person, weighing a gram or so, and within a distance that is 5 times the distance to the moon, the sail can reach a fifth of the speed of light. And after the first few minutes of the launch, the journey becomes very boring. It takes 20 years to reach the destination. And of course, you shouldn't aim it at where Proxima Centauri is now, but where it will be in 20 years. And then when this spacecraft reaches the destination, it could take a photograph of the planet and inform us whether it has life on it. And of course, there is another challenge, detecting the signal of this photograph from a distance of 4 light years. That's not trivial. And it takes 4 years for this signal to make it back to Earth. So altogether, 24 years. That's why I said, humans are not suited for interstellar travel, despite of what you see in science fiction movies. Equipment is. Now, there is another way to reach close to the speed of light, and that's if you park the sails close to a star that is about to explode in a supernova. If you put the same type of sail at about 100 times the Earth-Sun separation from a massive star that is about to explode, when the star explodes, there is a flash of light, and it can carry those sails up to the speed of light, as I showed in a paper that I published a couple of years ago. So this would be similar to surfers on the beaches of Hawaii being carried by a giant wave, except in this case, the wave is a wave of light. Another metaphor is dandelion seeds that you can see on the right-hand side that are carried by the wind. Now, we are probably not the sharpest cookies in the jar of the Milky Way. We are not the smartest. And why do I say that? Because I read the news every day. And I define intelligence as following the guiding principles of science, namely cooperation and sharing of evidence-based knowledge. And if you look at politics, we are not cooperating. We are not sharing, even if you look at academia, not just the public broadly. And the second thing we don't do very often is base our convictions on evidence. So we are not there yet. Perhaps that's why nobody contacted us. Once we reach the level where we follow evidence-based knowledge and we share it with everyone, perhaps we will hear a signal, welcome to the interstellar club of intelligent civilizations. So if I'm asked whether we are the smartest kid on the cosmic block, my guess is probably not, because the chance for that is the same chance as opening a random page in a recipe book and finding the best cake. I mean, what's the chance that if you take the soup of chemicals that existed on the early Earth, you get the pinnacle of creation, the best possible form of life? I mean, we are very proud of ourselves, but that doesn't mean much in the cosmic scene. And without prejudice, let's be open-minded and look up. And the first place to look is in our backyard. Turns out that in October 2017, the first object from outside the solar system was discovered by a telescope on Mount Haleakala in Maui, Hawaii, Pan-STARRS, and it was given the name Oumuamua, which means a scout in the Hawaiian language. You can see this object circled in blue in the middle of this image, and the stars are moving relative to it in the background. Now, one thing that was peculiar about this object was its initial velocity. It appeared to originate from the local standard of rest, which is sort of like the local parking lot of the Milky Way galaxy. It's the frame of reference that you get to when you average over the motions of all the stars in the vicinity of the sun. And the stars are moving relative to this frame at somewhere between 10 to 30 kilometers per second, typically. However, Oumuamua was nearly at rest in that frame. Only 1 in 500 stars is so much at rest as Oumuamua was. And that's unusual. So the motion of Oumuamua relative to the sun was simply the inverse of the motion of the sun relative to the local standard of rest. That was peculiar. And the sun, of course, kicked it out of that state. It was sort of like a buoy sitting at rest on the surface of the ocean, with the solar system being like a giant ship that collides with it. And as the object was tumbling every 8 hours, the amount of sunlight that it reflected changed by a factor of 10 or more. And that meant that the object has a very extreme shape. Most likely disc-like. You can see it from these two plots, which show the orientation, the possible orientations of the object for a disc-like configuration and a cigar-like configuration. So on the left, you see the disc-like case, and black means high likelihood, close to unity. And you can see that for most of the orientations, about 90% of them, you will end up matching the observational data for the light curve within the error budget. Whereas for a cigar-shaped object, only 15% of all cases match the data. So it was most likely flat, pancake-like. And then the Spitzer Space Telescope looked at it very deeply and didn't see anything. You can see the image on the top right. There is nothing, only noise in that image. And that meant that you can put very tight limits on carbon-based molecules or dust in the vicinity of this object. But at the same time, the object exhibited non-gravitational acceleration. There was a Nature paper in June 2018 that reported this excess push away from the sun. And if a comet were to derive this push from evaporation, about 10% of the comet mass had to be evaporated. We would see it with our eyes as a comet. But not only we didn't see that, there were no carbon-based molecules in the vicinity of the object. So clearly it was not a comet of the type that we have seen before. Yet it was pushed. And the question is, what provided this excess push, if not for the rocket effect? And the only thing that came to my mind was the reflection of sunlight. Because this push, this force away from the sun declined inversely with distance squared in a smooth way. There was no jitter as you usually expect from jets that evaporate non-uniformly on the surface of a comet. And there was no cutoff for the push at the distance from the sun where ice stops sublimating. But in order for sunlight to be effective in pushing such an object, it had to be very thin. And so I argued, nature doesn't make thin objects that are solid. And so maybe it's artificial in origin, just maybe. And that's really the fundamental question. Is Oumuamua natural or artificial in origin? And since then, in September 2020, there was another object discovered with the same telescope in Hawaii, Pan-STARRS. It was given the astronomical name 2020 SO, and it also exhibited an excess push away from the sun by reflecting sunlight with no cometary tail. Now, the astronomers that discovered it realized that if you extrapolate the trajectory back in time, actually this object came from Earth in 1966. It's actually a rocket booster that was launched into space by NASA as part of a lunar lander mission. And it had thin walls, and that's why it had a large area for its mass. So we know for sure that this object was artificial in origin because we produced it. The question is, who produced Oumuamua? And let me summarize the anomalies of Oumuamua. There was one anomaly that I didn't have time to describe, and that's just the abundance. A decade before it was discovered, I wrote together with Amaya Moore-Martin and Ed Turner from Princeton, a paper forecasting how many rocks we should expect from other stars to be discovered by the Pan-STARRS telescope, and we concluded nothing by orders of magnitude. So the discovery of Oumuamua was a surprise. It means there are many more objects than you expect based on what we know about the solar system. So that was a surprise. And then this object came from the local standard of rest. Only 1 in 500 stars is so much at rest in that frame. Its brightness changed by a factor of 10 as it was tumbling every 8 hours. And the best fit to the light curve is that of a pancake-shaped object. The Spitzer Space Telescope didn't detect anything. So given that we knew the trajectory, we could infer the surface temperature of this object, and then infer that the size must be smaller than 200 meters. And it couldn't have been smaller than 20 meters because a 20-meter object that is a perfect reflector would have given us the amount of light that we saw. So somewhere between 20 and 200 meters is where this object was. And since there was no outgassing, I suggested that it's being pushed by sunlight. Now, that proposal received a lot of pushback from the scientific community. And of course, most people just ignored the anomalies and said, it's natural, forget about it. There was even a group of people that came together in a review paper and said, it's natural, period. As if authority matters on such issues. It reminds me of a book that was written about Einstein's theory of relativity back in the early 1930s, where 100 authors came together to argue that relativity must be wrong. And when Einstein was asked about it, he said, why do you need so many authors? One of them could make a good argument and that would be sufficient. So there were, I should say, some people that paid attention to the anomalies and tried to explain them from a natural origin. And all of the suggestions made in this context invoked something that we've never seen before. For example, a dust bunny, a collection of dust particles in a cloud that is 100 times less dense than air. The problem with that is when such a cloud gets close to the sun, it will get heated by hundreds of degrees and will not maintain its integrity. The material strength of a cloud, think about it, is 100 times less dense than steam coming off your teapot. Then there was a suggestion that maybe it's an iceberg made of pure hydrogen, because if hydrogen evaporates, it's transparent and we can't see it. So it will be a comet whose outgassing we can't see. The problem with that proposal, first of all, we've never seen a hydrogen iceberg. We don't know if molecular clouds produce them, but moreover, they wouldn't survive the journey. They will evaporate very quickly within millions of years as a result of absorbing light from stars along their journey. Then there was a suggestion, maybe it's a nitrogen iceberg, chipped off the surface of a planet like Pluto. And there the problem is the mass budget. There is not enough nitrogen available in all the stars. And I should say that there was this original review paper arguing Oumuamua is natural. And then months later, the hydrogen iceberg hypothesis. And months after that, the nitrogen iceberg hypothesis. So my point is, if it was obvious that it's natural from the beginning, why would you need these additional papers? And what you see here are some numbers related to the evaporation of icebergs by either starlight or cosmic rays. In fact, what you see on the right-hand side is from a paper that was posted on the archive just yesterday. And what you find is, for a hydrogen iceberg on the left, the typical evaporation time as a result of absorption of starlight for an object the size of Oumuamua is millions of years. And within millions of years, at the typical speed of such objects through interstellar space, they can traverse only a distance of order hundreds of light years, or about 100 parsecs, which is only 1% of the size of the Milky Way galaxy. So, that makes it, that exacerbates the production rate that you need for these objects. You need a molecular cloud that is close enough that generated or produced Oumuamua, and most of them get evaporated along the way after they are born. Now, if you consider the nitrogen iceberg, it turns out that the lifetime from cosmic rays is not very different. It's at most 10 million years if you take the size to be similar to Oumuamua. And then if you want the cloud to survive for a fraction of a billion years, as assumed by the authors, the proposers of this model, then you need the object to start with a size bigger than 10 kilometers. So most of it gets evaporated. You are left just with a remnant that is much, much smaller in size. And then the mass budget problem is quite severe. So it turns out that even if you don't take this issue of evaporation into consideration, you need more nitrogen than you find in stars. So this model just doesn't carry the day. And here is the abstract of a paper that came out a couple of weeks ago by the authors of the hydrogen model, Daryl Seligman and Greg Laughlin. And I highlighted one of the sentences in the middle of the abstract, which basically says that hydrogen and nitrogen icebergs have serious difficulties in explaining Oumuamua. And that's our best bet in terms of a natural origin. I was actually asked at a colloquium last week, I was asked, suppose it is natural, suppose this object is natural, what would be your best explanation? And my reply was that we made an error in our measurement. That would be my best bet. Because if not, then the experience could be just like walking on the beach. Most of the time, you see rocks that are naturally produced. These are the comets and asteroids we have seen from the solar system. But every now and then, you see a plastic bottle. And that's Oumuamua. So you can think of the solar system as a mailbox. And it could collect packages that are technological from another civilization. Now, you might say, oh, my mailbox is empty. I don't want to go into the effort of checking it. And that would be the lazy approach. But that wouldn't make your mailbox empty. And perhaps if you check the mailbox, you will realize that there is a package there that carries an important message for the future of humanity, for the salvation of humanity. So if you didn't open it in time, you may follow the Darwinian selection of choosing only those intelligent civilizations that opened their packages in time to survive. We should check the mailbox. What's the big deal? We've searched for dark matter for 4 decades. Actually, Doug Finkbeiner works mostly on that. And, for 4 decades, we haven't found it. And we invested hundreds of millions of dollars searching in the dark. I remember as a young postdoc, the most popular view was that it's weakly interacting massive particles. Everyone was thinking, oh, it must be that. And we just didn't find it. Now, if it was weakly interacting massive particles of the type that we envisioned, it would have very little impact on our daily lives, except for the people who discovered that particle. They would get the Nobel Prize. But imagine finding a plastic bottle in space that was manufactured by another civilization. That would have a huge impact on humanity. So why would we spend 0 funds on this search? And gladly, I should say, with the Galileo Project, we have the money to do the search. It's not taken from money allocated to the search for dark matter. It's new money. And the effort that we are engaged in is just looking for evidence. So I just don't understand those who are still opposed to this project. That doesn't make any sense. Now, imagine a caveman going around and finding a cell phone. Now, the caveman is used to playing with rocks all of his life. So when he finds the cell phone, he would announce, this is a rock of a different type. Just like Oumuamua is a rock of a type that we've never seen before, a hydrogen iceberg or a nitrogen iceberg. The caveman would say, this is a shiny rock of a type that I've never seen before. But that's just the beginning of a learning experience. Because if the caveman presses a button, he may realize that it records his voice. And if he presses another button, it may record his image. And so by pressing buttons, we can learn more about these objects. And the way to figure out their nature is by getting more evidence. So rather than assuming that they are never seen before objects, they might be. And if we find that they are a nitrogen iceberg or a hydrogen iceberg, we learn something completely new about the interstellar medium, that there are nurseries of objects that are not produced in systems like the solar system, that are much more prolific in producing interstellar objects. And that would be important. So getting evidence is a win-win proposition. The second interstellar object that was discovered was named Borisov, after a Russian amateur astronomer, Gennady Borisov, who discovered it in August 2019, and it looked just like a comet. So I was asked, okay, the second object looks like a comet, it's natural. Doesn't it convince you that Oumuamua was also natural in origin? And I say, if you go down the beach and you see a plastic bottle, and after that you see a rock, that doesn't make the plastic bottle a rock. And of course, the best way to tell the difference is by taking a high resolution image, by getting close to it. Because they say a picture is worth 1,000 words. In my case, a picture is worth 66,000 words, the number of words in my book. I will need to write the book if we had a high resolution image. And we can get that. What you see here is an image taken by the OSIRIS-REx mission that came close to the asteroid Bennu and actually landed on it and scooped some material from it that it will return to Earth in 2023. So imagine getting such an image of an object like Oumuamua. We could easily tell if it's a hydrogen iceberg, nitrogen iceberg, or it has bolts and screws on it, an artificial object. And the one thing to recognize is that the cosmic play is not about us. You know, we just came at the end. The universe existed for 13.8 billion years. Our recorded history is just 10,000 years old. That's nothing. So we better be modest. Like, we shouldn't assume that if there is a visit, it's exactly right now, because our recorded history is just 10,000 years. Suppose it was 1 million years ago. We wouldn't know about it. There is no photo album from 1 million years ago. And we can find evidence for other civilizations, not just in the form of packages in our mailbox, but also in the form of industrial pollution of atmospheres. I wrote a paper about it in 2015. And by the way, astronomers are planning future telescope systems that would look for oxygen or methane in the atmospheres of habitable planets. But at the same time, they could look also for CFCs. If they find oxygen, by the way, the Earth for the first 2 billion years didn't have much oxygen in the atmosphere, even though there were microbes covering the Earth. We don't fully understand why there was a sudden jump in the oxygen level of the atmosphere. But the fact is that if we looked at Earth in the first 2 billion years, half of its life, we wouldn't necessarily conclude from a distance that it has life on it. And if we do find oxygen, you can also make it by natural chemical processes. So it will not be conclusive. But if we find CFCs, those molecules produced by refrigerating systems and industries on Earth, they cannot be produced naturally. And we would know that not only there is life, but there is industrial life on that planet. So why not use the same instruments? Yet if you look at the description of these future telescopes, nobody talks about industrial pollution. You can, in principle, also look for city lights on the night side of Proxima b. We wrote a paper about it a few months ago with an undergraduate from Stanford, Elisa Tabor. You can look for the reflectance of photovoltaic cells from the day side of Proxima b. You can look for flashes of light associated with beams that are used for propulsion of light sails. You can look for satellites that swarm around planets. So there are many ways to find technological signatures. And there is this paradox that Enrico Fermi posed about 70 years ago at lunch in Los Alamos. Where is everybody? That to me is very presumptuous, because it assumes that we deserve the attention, that they would come here and have a party in our backyard right now, even though we record history only for 10,000 years. And why would that be the case? It's quite possible that most of them are dead. They existed in the past, and by now their host star is not around anymore, or just like us, you know, they developed the means for their own destruction. So they survived only a few centuries of technological development. And trying to look for radio signals, which was the approach that the search for extraterrestrial technological civilizations took over the past 70 years, is not the right approach, because it's just like trying to have a phone conversation. You need your counterpart to be active. But if you look at Earth, most cultures that existed on Earth are not around anymore. We can find evidence for them through archaeological digs. And so we can do archaeology in space. look for civilizations that might not be around anymore. And if they sent AI systems, we could find them. And of course, to figure out their intent, we might need to use our own AI systems. It would be similar to using our kids to figure out content that we find on the internet, because they're much more computer savvy than we are. And my hope is that by finding relics of more advanced civilizations, we will change the way we behave. And the reason I say that is because if you look at human history, most of it was shaped by a group of humans trying to feel superior relative to other humans. The best example is the Second World War. The Nazi regime triggered the death of 75 million people. That's 20 times the number of deaths that were caused by the COVID-19 virus. Just think about it. A group of people decided to feel superior relative to everyone else and triggered the death of 3% of the world population in 1940. 3%. Now, if we do find another civilization that is far more advanced than we are, all of our genetic differences would be insignificant. And so my hope is that this will inspire us to ignore the small differences among us, between us, and convince us to cooperate as equal members of the human species. Thank you.
Thank you, Avi. Sorry that Zoom doesn't provide a good mechanism for you to hear everyone clapping.
I think Frank Laukian wanted to say something.
Sure, go ahead, Frank.
Yeah, hi, Avi. I think you said just about everything. Great presentation and lecture, of course. My pleasure to be a co-founder with Avi of the Galileo Project. I'm a visiting scholar in chemistry and chemical biology. That's also a long time ago. I got my chemical physics degree there. And yeah, no, I mean, looking for artifacts is just far more promising than looking for active radio signals. And Avi did say that we could look at artifacts that are 1 million or 1 billion or 3 billion years old. That compares very favorably compared to looking for active radio or laser signals from existing living extraterrestrial civilizations, if they exist and if they are in the 1 millionth of our galaxy. That's only our galaxy, not even the universe, that we could reasonably observe. So it's very important that we look for new plastic bottles or look through new telescopes. Maybe the only word of caution that I say is, I'm also involved in the Origins of Life initiative at Harvard, and we haven't cracked that problem yet, but creating life from the primordial soup of livestock molecules, but maybe in the next 10 years or so we'll succeed. I believe, but I don't know yet, that life may be almost universal and life may be almost inevitable on the right conditions on habitable exoplanets. But the jump to extremely intelligent and life with technological civilizations is still quite a jump. There are 5 million species on Earth today. There probably have been 500 million, but only one has mastered mathematics and the internet and astronomy and so on. And as Avi said earlier, we've only had a civilization really for 10,000 years out of the 4 billion years of life on Earth. So life may be abundant. Extraterrestrial civilizations may not be as abundant, but if we look for their artifacts, as Avi has proposed, we may have a chance of finding it, and it would obviously completely change our worldview and science in ways that are nearly unimaginable. So it's very exciting and an honor to be associated with this project, and thank Avi for his leadership.
Thank you, Frank.
Great, thank you. I see some hands. Let me actually start with Merrick's iPhone asked a question a few minutes ago. Is it possible that Oumuamua has been repelled by magnetic fields from the solar system, either because it's magnetized itself or acquired a charge somehow.
Yeah, well, the magnetic field from the sun drops as a dipole field as inversely with distance cubed. So it would have to be very fine-tuned to give you the push that of inversely with distance squared. And I don't see a simple way of doing that for an object that doesn't change its size.
Right. Okay. Ed Turner is joining us from Princeton, has his hand up.
Hi, Avi and all. As you know, I'm very enthusiastic about the Galileo Project, but let me ask a question from a slightly different point of view. As you know, Freeman Dyson, who not known for being a conservative thinker, argued decades back that the most effective way of finding evidence of extraterrestrial civilizations is not to look for them, but explicitly, but rather just to explore the universe as broadly as possible in hopes of stumbling over something, so surprising that you wouldn't attribute it to a natural object. Oumuamua is an example of that. We weren't looking for that. Your plastic bottles on the beach, you don't go out on the beach with predicting in advance what you might find there made by a civilization. You just go looking around and you stumble across something. So my question really is, are we being a little presumptuous to think that we can imagine in advance what signatures, either in terms of electromagnetic signals or in terms of artifacts, would most likely, by which a really advanced ETC would be most likely to reveal itself?
Well, that's an excellent question, because often we can imagine only things we experienced. And that limits our ability to imagine things different than us, life as we don't know it. In fact, I wrote a Scientific American essay on life as we don't know it. How do we find it? And one way to approach it is to look at anything that doesn't look, in the context, for example, of UAP, doesn't look like a bird, doesn't look like a drone, and doesn't look like a human-made military equipment, behaves in ways that are very strange. So then, by ruling out the possibilities that you are familiar with, you say, okay, that's intriguing. Let's get more detailed data on this thing. And eventually you figure out that it's outside of Earth, that it couldn't have been produced here. That's one way of finding it. In terms of biological life, it's even more complicated. And one way to expand our imagination is what Jack Shostak at Harvard is doing, which is to create synthetic life in the laboratory. Because once we create synthetic life in the laboratory, then we could change the conditions and see whether we get different forms of life. So just like in physics, laboratory experiments allowed us to unravel the laws of physics over the past century. That's how we figured out how the universe works. It was from laboratory experiments. And the amazing finding is the same laws of physics that we find in our laboratories operate throughout the universe. By the way, this is not to be taken lightly. We often assume that to be the case, but it's quite remarkable that the universe is so organized, because when we decide on a set of laws in society, you find a lot of people that disobey them. So why does the universe at large obey the same strict laws, the physical reality? That's remarkable. But with respect to life, we can also expand our imagination, our understanding of life as we don't know it, from doing laboratory experiments and figuring out. And I should say, the main message that I have is that we should be modest. We should not assume that we know the answer in advance. And, a sense of modesty is really needed, because just over the past few months, you saw people like Jeff Bezos and Richard Branson lifting their body by 1% of the Earth radius and being very proud of that, using their wealth. But if you think about it, bragging in space is an oxymoron. Showing off in space is an oxymoron, because space is vast. The size of the observable universe is 10 to the power 19 times bigger than the radius of the Earth. So in the same spirit of modesty, we should not assume that we know in advance what's out there. Most importantly, we should look through our windows rather than argue that there is nothing out there and we need extraordinary evidence before we engage in a search through our mailbox for any mail, because you would never find the extraordinary evidence if you don't search. It's a circular argument that was often repeated by people. You know, we would never find gravitational waves if we didn't invest, if the National Science Foundation didn't invest $1.1 billion in LIGO. Before the investment, no gravitational waves were detected directly. And so my point is, we have to invest funds and effort before we can argue that there is no extraordinary evidence. Just saying we need the extraordinary evidence before investing the funds doesn't make any sense.
Okay, I'd like to bring up a comment and a question from the chat and then go to Daryl Seligman. So the comment is, a good analogy might be plastic shopping bags. There are a lot of them and they blow around in the wind everywhere. And so, you know, we might be found by our detritus in that sense. That's kind of nice.
That's an excellent point, and I actually mentioned it in my book as space trash. You know, by the way, space trash. Speaking about space trash, you can imagine a very advanced civilization deciding not to engage with us because it would lower their quality of life. So they may close themselves in the cocoon, and you might say, okay, but then we can discover them. But the answer is the second law of thermodynamics implies that they must throw some trash out. And we can be just like those investigative journalists that look through the trash cans of celebrities in Hollywood and trying to find something about their private lives.
Nice. There was a question about debris in the way, either interrupting the path of the sail or the laser beam that's propelling it. So I guess that could be interstellar dust, or it could be anything else in the way.
Yes, so we studied that in a paper with Thim Huang, where we, and also originally in the paper I wrote with Shmuel Bialy on Oumuamua. And for objects moving at the kind of speed that Oumuamua was moving, there is not much damage encountered by dust colliding with it. At the speed of starshot, a fifth of the speed of light, every atom colliding with the surface at a fifth of the speed of light releases the amount of energy similar to a nuclear explosion per unit mass. Okay, so you get a lot of energy, you get these craters from dust particles, but we calculated that they are very rare because space is quite diluted. And with a coating of a few millimeters, you can protect the electronic equipment.
Okay, yeah, that's good. I think we should take two more questions and then kind of formally end the presentation, but we may keep the Zoom session going if other people want to hang around. So let's go to Daryl Seligman.
Hey, Avi, nice talk. I was just wondering, with the Galileo project, how do you think do you have any concrete plans yet, what the best way to look for more interstellar objects would be?
Yeah, I mean, obviously the Vera Rubin Observatory will be much more sensitive than Pan-STARRS, so hopefully it will give us the alerts for objects, you know, a year or more before they get to us, so that we can design a space mission to visit them. The problem with Vera Rubin Observatory is SpaceX. It would launch these communication satellites, tens of thousands of them, and they would reflect sunlight and sort of interfere with our observations of interstellar objects, because SpaceX is basically putting city lights in the sky. Astronomers try to avoid cities by going to mountaintops, but SpaceX is putting city lights. And we will have to resolve that issue by painting them black or something else. Now, aside from the Vera Rubin Observatory, I should say that there might be space missions that will put telescopes in other locations, such that, you know, if another telescope is far from Earth, it could, for example, together with a telescope on Earth, pinpoint the trajectory to a much higher precision by parallax. And then we can tell easily if there is an excess propulsion and how the object looks from different directions. So I'm very hopeful that such things will come to fruition, and people are talking about it. I don't have time to get to details. So I think overall, a space mission designed to look after the next few objects that are as weird as Oumuamua was could help us a lot in figuring out the nature of these objects. And based on rough estimates, as you know, we should see of order 10 or so Oumuamua-like objects with the Vera Rubin Observatory if they move on random trajectories throughout the solar system. Now, if they were directed at the habitable zone and they don't move on random trajectories, there may be a while before we see the next one.
Okay, thanks. That's great.
Thanks. And Gary Melnick.
Thank you, Avi. Very interesting talk. Under the category of humility in our efforts, I'll relate a story that Carl Sagan was fond of relaying to us graduate students in the 1970s. Carl, of course, was at the forefront of trying to send signals along with Frank Drake, who was also at Cornell at the time, in the hopes of receiving a reply. But he was very humble about the prospects of receiving an answer. And the story he would tell was of a conversation Carl had with Margaret Mead, the anthropologist, who in the early 70s came across a tribe that had had no contact with the outside world. They were distributed among a half dozen small islands in the South Pacific, and they communicated by going to the high point on the mountaintops of their respective islands and building a fire and sending a sort of a crude form of Morse code by putting palm fronds over the fire and creating dots and dashes with the smoke, with the intention of telling their compatriots among these closely spaced islands where the fishing was good and when they wanted to visit. But Margaret Mead, once she made contact with these people, found out that they were interested, as we are, in knowing if they were the only people in the world. And so what they did was they selected among their late teens and early 20s individuals who had the most acute eyesight. And they took them to the highest peaks and they looked out over the horizon, concluding there was nobody else out there because they saw no other smoke signals. While at the same time, they were being pierced by millions of radio and television signals. So here we sit with our listening devices, trying to detect other civilizations with our current technology, while God knows what, neutrino beams, communications with, who knows what, tachyons are flowing past us. So I think it all comes under the category, as you mentioned, of a certain degree of humility in our efforts here.
I completely agree with you. I would just add an anecdote about, a fisherman that realized after going on an expedition that he discovered a new law of nature, that all fish are bigger than 2 inches, until he realized that that's the size of the hole in his fishing net.
Right.
So much of what we see in astronomy is a selection effect, and thus we're extremely careful. All right, well, that was a very stimulating and compelling argument in favor of interstellar archaeology. So thank you, Avi, again. And let's maybe end the formal part of the presentation